Right now, as you watch this video, the data reaching your screen did not float down from a satellite hovering in space. It travelled through a cable thinner than a garden hose, lying in near total darkness at the bottom of the ocean. That is not a metaphor. That is literally what happened. The idea that the internet lives in the cloud is one of the most successful illusions in modern life. The cloud is a marketing word. The physical reality is a web of undersea fiber optic cables stretching roughly 1.3 million kilometres across the ocean floor, carrying somewhere between 95 and 99% of all international data traffic on Earth. Every email, every video call, every financial transaction moving between continents almost certainly pass through one of these cables. Satellites do exist, and they serve important roles, but they are too slow and too limited in capacity to carry the sheer volume of information the modern world demands. Fiber optic cables transmit data at nearly the speed of light and can carry hundreds of terabits per second down a single line. Satellites simply cannot compete with that. So the next time someone tells you their data is safely stored in the cloud, you can politely inform them that their cloud is actually resting on the seafloor somewhere between continents, wrapped in a layer of protective plastic and steel, being occasionally nibbled on by curious deep-sea creatures. We will get to that part. But first, this whole system did not appear overnight. The story of undersea cables is older and stranger than most people realize, and it starts long before the internet existed. Before there was internet, before there was telephone, there was the telegraph. And before the telegraph could cross an ocean, engineers had to do something that most people in the 1850s thought was completely impossible. They had to lay a cable across the Atlantic. The first successful transatlantic telegraph cable was completed in 1858, connecting Ireland to Newfoundland in Canada. It was a monumental engineering achievement that took years of failed attempts and enormous financial risk. Queen Victoria and President James Buchanan exchanged messages across the Atlantic for the first time in history. The cable worked for about 3 weeks before it failed entirely. It took another 8 years and multiple expeditions before a reliable transatlantic cable finally held. But when it did, the time it took to send a message from London to New York dropped from about 10 days, the time a ship needed to carry a letter, to just a few minutes. The entire rhythm of global business and diplomacy changed almost instantly. That Victorian-era infrastructure is the direct ancestor of what we use today. The principles are different: copper wire replaced by glass fibers, Morse code replaced by pulses of laser light. But the concept of physically connecting continents through cables laid on the ocean bottom is exactly the same idea. Modern cables carry data using pulses of light fired through strands of glass so pure that if you stretched one into a wall of solid glass, you could see clearly through 70 kilometers of it. The light travels in total internal reflection, bouncing along the fiber without escaping, arriving at the other end almost as strong as it started. It is one of the most elegant feats of physics ever put to practical use. Laying a modern undersea cable is an operation of almost absurd complexity. It begins months before a single meter of cable touches the water. Teams of geologists and oceanographers spend enormous amounts of time mapping the route, looking for underwater mountains, earthquake fault lines, volcanic zones, and shipping anchor paths to avoid. The cable itself is manufactured in long segments and loaded onto specialized ships called cable-laying vessels. These ships are enormous, capable of carrying thousands of kilometers of cable wound onto giant drums below decks. The cable is fed off the back of the ship slowly and deliberately as the vessel moves across the ocean. At the surface, the cable is about as thick as a human wrist, reinforced with layers of steel wire to protect against fishing trawlers and ship anchors near coastlines. As the depth increases and the pressure hazards decrease, the cable gets progressively thinner. In the deepest parts of the ocean, the cable is roughly the diameter of a standard garden hose. The entire length of a major transoceanic cable can weigh millions of kilograms. Laying it is a process that can take weeks or even months and costs hundreds of millions of dollars. Once the cable reaches shore, it comes up through a pipe buried in the seafloor and connects to a landing station, usually a nondescript building sitting on a beach somewhere that looks nothing like the global communications hub it actually is. These landing stations are among the most strategically critical pieces of infrastructure on the planet. Damage one, and entire countries can lose a significant portion of their international connectivity in an instant. For all the engineering brilliance that goes into building and laying these cables, nature and human accident have a stubborn habit of breaking them. The list of things that can damage an undersea cable is surprisingly long and occasionally absurd. Ship anchors dragging along the shallow seafloor are responsible for a significant portion of cable cuts every year. Fishing trawlers with heavy nets scraping the bottom cause damage too. Undersea earthquakes and landslides can snap cables cleanly in places where no ship has ever gone. In 2006, a massive earthquake near Taiwan triggered an undersea landslide that severed 9 different cables simultaneously, severely disrupting internet service across Southeast Asia for weeks. And then there are the sharks. In the 1980s and again in the 2000s, sharks were documented biting into early fiber optic cables. The leading theory is that the electromagnetic fields generated by the cables may attract them, since sharks are highly sensitive to electrical signals through specialized organs in their heads. Modern cables in shark-prone regions are now wrapped in an additional layer of steel wire mesh specifically to deter this. Beyond natural hazards, there is also the very deliberate threat of sabotage. Undersea cables have been cut by hostile actors throughout history. During World War I, Britain cut Germany's transatlantic cables within hours of declaring war. Today, military analysts consider undersea cable networks a critical vulnerability in global infrastructure, and there are persistent concerns about vessels from various nations surveilling or threatening cable routes. The entire system that keeps the modern world connected hangs quite literally by threads. Despite all the risks, undersea cables are not going anywhere. In fact, the opposite is true. The demand for global bandwidth grows every single year, and new cables are constantly being planned, funded, and laid. What has changed dramatically in recent years is who is paying for them. For decades, cables were largely built by consortiums of telecom companies sharing costs and capacity. Today, some of the biggest investors in new undersea cable projects are technology companies like Google, Meta, Amazon, and Microsoft. Google alone has invested in over a dozen major cable projects around the world. These companies need so much bandwidth to serve their global platforms that it makes more financial sense for them to own the cables outright rather than lease capacity from telecoms. Some newer cables represent extraordinary advances in capacity. The Amity cable, for example, connecting the United States and Europe, can carry around 400 terabits of data per second. To put that in perspective, that is enough bandwidth to stream millions of simultaneous ultra high-definition videos without breaking a sweat. And engineers are still pushing further. Researchers are experimenting with cables that carry multiple separate channels of light at different wavelengths simultaneously, multiplying capacity without laying new cable. The ocean floor is quietly becoming the most valuable real estate in the world, not for what is on it, but for what runs across it. The next time you stream a video, send a message, or just open a web page, take a second to appreciate the wild, invisible journey your data just completed. If you find yourself fascinated by the hidden systems quietly running the modern world, hit that like button and subscribe, because there are so many more extraordinary stories exactly like this one waiting for you here.